Now I will show you how we use the data structures to compute a theory on the basis of a set of axioms. So I show you first a simple set of axioms. Axioms with variables this time. So, okay. This is a set of axioms about an operation which is reflexive, commutative, and transitive. Okay, and then I will use the axioms to compute a representation of all terms using a number of constants that can be built for this operation. Okay. So I will consider just two variables, two constants, okay, and okay. So here are the set of structures that are created. You can see that we have three sets. We have three sets of structures representing all terms that can be built given A and B. And in fact, all of them are equal either to A or B or AB. Okay. So we have three sets of structures. And here, for instance, we can see that any term containing only B on the left of the operation and only B on the right of the operation are equal to B. But here we have much more terms that are equals to AB. Instead, for instance, here the term which contains A and B on the left and only B on the right is equal to AB. Okay, I can simplify, for instance, this one. It simplifies to AB. If I want to simplify this one, it simplifies to B. Okay? So it's quite simple. Now I show you how the algorithm works. In fact, so I will rerun the same program with with some parameters. I think this is okay. So we see that in fact the algorithm generates all sequences of a set of structures identifiers. So we have at the beginning we have A and B, but also AB. So we have three sets of identifiers. So we will generate all sequence containing 1, 2, or 3, and we will we will in fact instantiate the axioms by replacing the variables by the set identifiers. And it will create new structures belonging to new sets of identifiers. And then for each axiom, we will unify the two sets. We will put the two sets together. And this will reduce the number of sets. And also, it will rename some structures. Because when we put two sets together, we remove one set identifier and also all structures of these sets, but we replace them by new structures where the old identifier is replaced by the new identifier of the set to which it is unified. Okay? And doing so, we will create more and more sets, but they will be reduced at the end, at least in the whole theory as a finite representation. Okay. So now we will apply this for Boolean expressions. So I consider a set of axioms for Boolean expressions. So this one, okay. Sorry for the French comments. This is a set of axioms for the Boolean calculus. In fact, it is not completely minimal because this one is more efficient than a completely minimal set, but it is still small. Okay. So I will apply the same algorithm to this set of axioms. Okay, and also I will use 3 propositional variables A, B, C. So we will generate all Boolean formula involving A, B, and C. Oh, I'm sorry. So it takes 5 minutes to compute all terms. And you can see that it is correct, since we have computed, at the end we have 256 sets, and it's okay because there are in fact two exponents, 3 different equivalence classes, and also it is easy to check that this is the number of structures that we should have computed.